I want to start with a confession. In all my years of studying the cosmos, in all the lectures I have given, and all the books I have written, and all the conversations I have had with the greatest minds in theoretical physics, there is one question that has never stopped making the hair on the back of my neck stand up. One question that every time I think I have made peace with, it reaches back out of the dark and grabs me by the collar and reminds me that we do not know nearly as much as we think we do. What is inside a black hole? Not what is near a black hole, not what happens at the edge of a black hole, not what a black hole does to the space and time around it. I mean, what is actually at the bottom, at the center, at the place where everything, the matter and the light and the information and the history of whatever fell in ends up what is there. For decades, the answer that physics gave us was simultaneously the most honest and the most unsatisfying answer in all of science. We do not know further. And furthermore, our best theories tell us that at the center of a black hole, the laws of physics, as we understand them, break down entirely. Curvature, the equations produce a result called a singularity, a point of infinite density, infinite gravity, infinite curvature of space-time. And in mathematics, when your equation produces infinity, it is not telling you that something infinite exists. It is telling you that your equation has failed, that you have pushed your theory beyond the domain where it is valid, that something is happening that your framework cannot describe. The singularity at the center of a black hole is physics waving a white flag. It is the universe telling us that our understanding is incomplete. That general relativity, which is the most precisely tested theory in the history of science, which has passed every experimental test we have thrown at it for over a century, which predicted the existence of black holes and gravitational waves and the expanding universe, that theory runs into a wall at the center of a black hole and stops working. But here's what I want you to understand about that. The fact that our theories break down is not a failure, it is an invitation. Every time in the history of science that a theory has broken down at some extreme limit, it has meant that something new and deeper and more fundamental was waiting to be discovered. Newton's laws broke down at velocities close to the speed of light. And that breakdown led Einstein to special relativity. Special relativity and classical mechanics broke down at the scale of atoms and molecules. And that breakdown led to quantum mechanics. General relativity breaks down at the singularity. And that breakdown is pointing us towards something we do not yet fully have. Something that when we find it will almost certainly be the most profound advance in our understanding of the universe. Since Einstein sat in his patent office in Bern and started thinking about what it would be like to ride alongside a beam of light. And here is the news. The genuinely extraordinary news that has been coming out of theoretical physics over the past decade or so. We are getting closer, not in the sense that we have definitively answered the question. We have not. But in the sense that a convergence of ideas from quantum mechanics and general relativity and information theory and string theory and holography is beginning to paint a picture of what might actually be happening inside a black hole. A picture that is so strange and so radical and so different from anything our intuitions prepare us for, that it makes the weirdness of quantum mechanics look like common sense speak. So that is what we are going to do today. We are going to go inside as far as the physics will take us. And I promise you that by the time we are done, the universe will look different to you than it did when we started. Not slightly different. It's fundamentally different in a way that I think will stay with you. But first, I need to make sure you understand what a black hole actually is. Because the popular image of a black hole is almost always wrong in ways that matter for everything that follows. A black hole is not a hole. It is not empty. It is not a vacuum cleaner sucking up everything around it. It is not a tunnel to somewhere else. At least not in any simple sense. A black hole is a region of space where gravity is so strong that nothing, not even light, can escape. That is it. That is the definition. A region of space defined entirely by the behavior of gravity. The boundary of that region has a name. The event horizon, and the event horizon is one of the most profound concepts in all of physics because of what it means for information. The event horizon is the point of no return. Cross it, and you are inside forever. Not because there is a wall there, not because there is anything physically special at the event horizon itself. If you were falling into a sufficiently large black hole, you would cross the event horizon without feeling anything unusual. No alarm would go off. No physical sensation would mark the moment. You would simply cross an invisible line in space. And from that moment forward, every path available to you in space-time would lead inward toward the center, toward the singularity. You could not turn around any more than you can turn around in time and go back to yesterday. Now the size of the event horizon depends on the mass of the black hole. The event horizon of a black hole with the mass of the sun would be about 3 kilometers across. 3 kilometers. The sun itself is about 1.4 million kilometers in diameter. You would have to compress all of that mass into a sphere 3 kilometers across, and you would have a black hole. The event horizon of the supermassive black hole at the center of our galaxy. Sagittarius A star, which has a mass of about 4 million suns, is about 24 million kilometers. It's across the event horizon of the black hole at the center of the galaxy, M87, the one we actually imaged with the Event Horizon Telescope in 2019, is larger than our entire system. And by the way, that image, that first actual photograph of a black hole shadow, that blurry orange ring that appeared on every screen on Earth on the 10th of April 2019, I want to tell you what that image represents, because I do not think most people fully appreciated it. We took a photograph of an object 55 million light years away, an object whose event horizon is 38 billion kilometers across. We resolved a feature that subtends an angle of about 40 micro arcseconds on the sky. To give you a sense of what that means, that is equivalent to photographing an orange sitting on the surface of the moon from Earth. with a telescope the size of the Earth itself, assembled by linking radio observatories on 6 continents into a single instrument. That image is one of the greatest technical achievements in the history of science. Butters. And what it showed us was exactly what Einstein's equations predicted more than a century before we had the technology to check. Blas. But the image shows us the outside, the event horizon, and the glowing material around it. It tells us nothing about what is inside. That is a different question, a harder question, and that is the question we are here to explore. So let us go in. Imagine you are in a spacecraft far from a black hole, far enough that you can observe it safely. You watch a colleague in another spacecraft fall toward the event horizon. Here's what you see. As your colleague approaches the event horizon, the light coming from their spacecraft gets redder and redder. The gravitational field of the black hole is stretching the wavelength of the light, making it redder, making it dimmer. And the spacecraft appears to slow down. From your perspective, watching from outside your colleague never quite reaches the event horizon. Their image gets dimmer and redder and more frozen in time, asymptotically approaching the event horizon, but never crossing it. Eventually, their image fades below the threshold of detectability. They appear to stop at the edge of forever. Now, here is where it gets interesting. From your colleague's perspective, inside the falling spacecraft, the experience is completely different. They feel no special force at the event horizon. They cross it. They keep falling. And then the center approaches, and as the center approaches, things get bad, very bad. Because as the tidal forces, the difference in gravitational pull between your head and your feet increase, the person gets stretched along the radial direction and compressed perpendicular to it. Physicists call this process spaghettification. And yes, that is the actual technical term used in peer-reviewed papers. The person is stretched into a long, thin strand of matter, like cosmic pasta, as they approach the singularity. At least that is what general relativity tells us happens. But here is the problem. General relativity might not be telling us the full story. And this is where the real mystery begins. Because there is another theory in physics that has something to say about what happens inside a black hole. And that theory has a fundamentally different picture of what matter and space and information are at the smallest scales. That theory is quantum mechanics. Quantum mechanics is the theory of the very small atoms, electrons, photons, the fundamental particles and forces that make up everything. Their quantum mechanics is weird in ways that took the greatest minds of the 20th century decades to come to terms with. Albert Einstein never fully made peace with it. He famously said, God does not play dice with the universe in objection to the fundamental randomness that quantum mechanics says is built into the fabric of reality at the smallest scales. And yet, quantum mechanics works. It works with a precision that is almost beyond comprehension. The predictions of quantum electrodynamics, the quantum theory of electromagnetism, have been verified experimentally to a precision of 1 part in a trillion. If you were to measure the distance from New York to Los Angeles using the accuracy of quantum electrodynamics, you would be correct to within the width of a human hair. Quantum mechanics and general relativity are the two most precisely tested theories in all of science. They're both extraordinarily successful in their respective domains, and they are fundamentally incompatible with each other. Not just in the sense that they give different answers to some questions. They are built on assumptions about the nature of reality that cannot both be true simultaneously. General relativity describes gravity as the curvature of space-time, a smooth, continuous, geometric structure that bends in the presence of mass and energy. Quantum mechanics says that everything at the smallest scales is fundamentally discrete and probabilistic. Energy comes in chunks called quanta. Position is not definite until measured. The vacuum itself is not empty but seething with quantum fluctuations. Virtual particles popping in and out of existence on timescales, so short that the uncertainty principle allows it. How do you reconcile a smooth, continuous, curved space-time with a fundamentally discrete quantum reality? That is the problem of quantum gravity. And it is the central unsolved problem in all of theoretical physics. The holy grail, the unification that physicists have been chasing since the 1930s, and the place where its solution matters most. The place where we need both theories simultaneously and where their incompatibility is most glaring and most consequential is inside a black hole at the singularity, where the density and the curvature of space-time become infinite and quantum effects cannot be ignored. The singularity is where quantum gravity lives. Where quantum gravity must be applied, quantum, and where we do not yet have a theory of quantum gravity that we fully trust. So when we ask what is at the bottom of a black hole, we are asking what quantum gravity tells us is there. Problems. And the answer to that question is one of the most contested and fascinating open problems in all of science. Now I want to tell you about the information paradox, because this is the problem that has been driving the most exciting theoretical work on black holes for the past 50 years. And it is the problem whose attempted solutions have led to some of the most radical and mind-bending ideas in all of physics. The information paradox was identified by Stephen Hawking in 1974. Coals. And it starts with one of Hawking's greatest discoveries. Black holes are not entirely black. Here is what Hawking showed. At the event horizon of a black hole, quantum effects cause the black hole to emit radiation. Not because matter is escaping from inside the event horizon. Nothing escapes from inside the event horizon. But because of the way quantum fields behave in the curved space-time near the event horizon, virtual particle-antiparticle pairs that are constantly popping in and out of existence, everywhere in the quantum vacuum, sometimes pop into existence right at the event horizon, with one particle just inside and one just outside. The one outside escapes as real radiation. The one inside falls in and carries negative energy that reduces the mass of the black hole. The black hole slowly loses mass, slowly radiates, slowly evaporates. This radiation is called Hawking radiation. And it has never been directly detected because for black holes of astrophysical size, the temperature of the Hawking radiation is fantastically small. For a black hole with the mass of the sun, the Hawking temperature is about 60 billionths of a Kelvin. Utterly undetectable against the background radiation of the universe. But the theoretical prediction is on extremely solid ground. It follows from combining quantum field theory with general relativity in a regime where both can be applied without full quantum gravity. It is the most robust result we have from the frontier where the two theories meet. Now, here is the paradox. Hawking radiation appears to be completely random, completely featureless. It carries no information about what fell into the black hole. The radiation from a black hole that formed from collapsing stars looks identical to the radiation from a black hole that formed from collapsing books or collapsing computers or collapsing anything. The black hole has no hair, as physicists say. It is characterized only by its mass and spin and electric charge. Everything else about what went in is lost. Right. But quantum mechanics has a fundamental principle that says information cannot be destroyed. In quantum mechanics, the evolution of a physical system is always in principle reversible. Given complete knowledge of the final state of a system, you can always, in principle, calculate its initial state. Information is conserved. This is not a minor technical detail. It is built into the mathematical structure of quantum mechanics at the deepest level. It is connected to the unitarity of quantum evolution. And if unitarity fails, if information can genuinely be destroyed, then quantum mechanics itself breaks down. So here is the paradox. If Hawking is right, that black holes evaporate completely and the radiation carries no information about what went in, then information is destroyed. Quantum mechanics is violated. If quantum mechanics is right and information is conserved, then either Hawking's calculation is wrong or the information somehow escapes in the Hawking radiation, which seems impossible given that the radiation originates outside the event horizon and has no access to what is inside. For decades, this paradox seemed completely intractable. It was not just a technical problem. It was a fundamental conflict between two of our best theories about the nature of reality, paradox. And the resolution of this paradox is what has been driving some of the most creative and radical theoretical thinking in physics over the past 2 decades by Beck. And those attempts at resolution have led us to ideas that are genuinely staggering in their implications. Let me tell you about 3 of them. And I want you to brace yourself, because each one is more mind-bending than the last. The first idea is the holographic principle, and it comes from a direction that nobody expected. In the 1990s, physicists Jacob Bekenstein and then Stephen Hawking made a remarkable discovery about black holes. The entropy of a black hole, the measure of its information content, its disorder, is proportional not to its volume, but to the area of its event horizon. Not the volume, the area, the surface the two-dimensional surface area of a three-dimensional object encodes all of its information content. Think about what that means. Take a black hole with a certain volume of space inside it. The information that describes everything inside that volume is not stored in the volume. It is stored on the surface that surrounds it like a hologram. A hologram is a two-dimensional surface that encodes a three-dimensional image. You can reconstruct the three dimensions from the two-dimensional information. The black hole seems to work the same way. Everything inside is encoded on the outside and then physicists Juan Maldacena and others extended this idea into something even more radical. The holographic principle, the idea that not just black holes, but the entire universe might be a hologram. The three-dimensional space we experience might be a kind of projection of information encoded on a two-dimensional surface at the boundary of the universe. That the fundamental reality might be two-dimensional, and the three-dimensional world we inhabit might be emergent. A higher dimensional image projected from a lower dimensional reality. I want to pause here because I know this sounds like science fiction. I know it sounds like the kind of thing that belongs in a philosophy seminar rather than a physics paper. But the holographic principle is not speculation because it is supported by one of the most mathematically precise and extensively tested correspondences in all of theoretical physics. The ADS CFT correspondence discovered by Maldacena in 1997, a precise mathematical duality between a theory of gravity in a certain kind of space-time called anti-de Sitter space and a quantum field theory with no gravity living on the boundary of that space-time. The two theories are mathematically equivalent. Every calculation in one corresponds to a calculation in the other. The gravity theory and the no gravity theory are two descriptions of the same physical reality. And what this correspondence tells us about information in black holes is profound. In the boundary theory where there is no gravity and quantum mechanics is fully valid, information is manifestly conserved. It cannot be destroyed. Because the bulk theory with gravity and black holes is equivalent to the boundary theory, information must be conserved in the black hole too. Somehow, through some mechanism, we do not yet fully understand the information that falls into a black hole must be preserved, must eventually escape, must be encoded in the Hawking radiation in some subtle way that Hawking's original calculation missed. The holographic principle does not tell us exactly how the information escapes. That is still being worked out. But it gives us a framework within which the paradox is resolved in principle. And the resolution requires us to accept something extraordinary. That the interior of a black hole and its exterior are not as separate as they seem. That the information inside is in some sense also outside. Insist that the radical distinction between inside and outside that our intuitions insist upon may not be fundamental party. Which brings me to the second idea. And this one I want you to really feel. Not just understand. Feel. It is called the ER equals EPR conjecture. And it connects two things that Einstein discovered in 1935 that seem to have absolutely nothing to do with each other. ER stands for Einstein-Rosen. In 1935, Einstein and his colleague Nathan Rosen showed that the equations of general relativity have a solution that connects two separate regions of space-time through a kind of tunnel, a bridge, a throat of curved space-time that links two distant points or even two separate universes. We call this an Einstein-Rosen bridge. You might know it by its more popular name, a wormhole. This EPR stands for Einstein-Podolsky-Rosen. Also in 1935, Einstein and his colleagues Boris Podolsky and Nathan Rosen wrote a famous paper pointing out what seemed to them like a paradox in quantum mechanics. If two particles interact and then separate, they can be in what quantum mechanics calls an entangled state. A state where measuring one particle instantaneously affects the state of the other, no matter how far apart they are. Einstein hated this. He called it spooky action at a distance, and he thought it proved quantum mechanics was incomplete. As it turned out, quantum mechanics was right, and Einstein was wrong about this. Quantum entanglement is real. It has been verified experimentally countless times. Entangled particles really do exhibit correlations that cannot be explained by any local hidden variable theory. The universe really is spooky in this way. 8p. Now, in 2013, physicists Juan Maldacena and Leonard Susskind proposed something breathtaking. ER equals EPR. The wormhole and the entanglement are the same thing. Two entangled particles are connected by a microscopic wormhole. Quantum entanglement is not just a correlation, it is a geometric connection, a thread of space-time linking two particles no matter how far apart they are, black holes. And if that is true, then consider what it means for a black hole. As a black hole evaporates, the Hawking radiation that escapes is quantum mechanically entangled with the interior of the black hole. If ER equals EPR is correct, then that entanglement corresponds to a geometric connection, a wormhole connecting the interior of the black hole to the Hawking radiation outside it. The inside and the outside are connected not through the event horizon in the traditional sense, but through the quantum geometry of entanglement, through microscopic threads of space-time that link what is in to what is out. This is called the ER equals EPR conjecture, and it is one of the most audacious ideas in contemporary theoretical physics. It suggests that space-time itself might be built from quantum entanglement, that the geometry of the universe is woven from the quantum correlations between its parts. That when you untangle entanglement, you are not just breaking a correlation between particles, you are tearing the fabric of space-time. Think about that for a moment. Space-time emerging from entanglement, geometry emerging from quantum correlations. The smooth, continuous fabric of the cosmos that general relativity describes, built up from the probabilistic quantum connections between its parts. This is the frontier. This is where the greatest minds in theoretical physics are working right now. And it is pointing toward a picture of reality that is more unified and more strange and more beautiful than anything we have had before. And now the third idea, the one that answers most directly the question we started with: what is at the bottom of a black hole? The answer that some physicists are beginning to take seriously is this: another universe. I want to let that sit for a moment before we dive into the physics, because I think it is worth acknowledging how extraordinary it is that this sentence can be written not as science fiction, but as a serious proposition being explored by serious physicists using serious mathematics in peer-reviewed journals. The idea that a black hole might contain another universe. That the singularity at the center might not be an ending, but a beginning. That what looks from the outside like the most destructive object in the cosmos might from the inside look like the birth of an entirely new space-time. This is where the physics is pointing. Not with certainty, not with the kind of experimental confirmation that lets you call something established science, but with the kind of mathematical coherence and theoretical motivation that historically has preceded the great revisions in our understanding of reality. Praise. So let us follow the thread. We left off with the holographic principle telling us that information is preserved, with ER equals EPR telling us that the interior and exterior of a black hole are connected through quantum entanglement woven into the geometry of space-time itself. Quantum, and with the question of what the equations of quantum gravity tell us, is actually happening at the singularity, where general relativity breaks down and waves its white flag. To answer that question, I need to tell you about what happens when you apply quantum thinking to the singularity. When you take seriously the idea that even space-time itself must obey the rules of quantum mechanics at the smallest scales. General relativity tells us that at the singularity, the curvature of space-time becomes infinite. The density becomes infinite. Everything breaks down. But quantum mechanics has something to say about infinities. Specifically, quantum mechanics tends to smear things out. The uncertainty principle says you cannot simultaneously know the position and momentum of a particle with perfect precision. The more precisely you know one, the less precisely you can know the other. And this smearing has a physical consequence. It prevents things from being perfectly localized. It prevents infinite densities. It softens singularities. When physicists attempt to apply quantum corrections to the equations of general relativity near the singularity, something remarkable happens. In some approaches, particularly in a framework called loop quantum cosmology, the quantum corrections generate a repulsive force at extremely high densities, a force that opposes the crushing gravitational collapse, a force that grows stronger the more compressed the matter becomes. And at densities near what is called the Planck density, the density at which quantum gravity effects become dominant, the repulsive force becomes strong enough to halt the collapse. The singularity does not form. Instead, the collapsing matter reaches a maximum density and then rebounds. It's thickened. It bounces, bounds. And what does the bounce produce? If the collapsing matter does not form a singularity, but instead rebounds under quantum gravitational pressure, it expands. It expands into something, into a new region of space-time that is causally disconnected from the black hole's exterior. A region that from the inside looks like the beginning of an expanding universe a Big Bang. Our Big Bang, be careful. Now, I want to be careful here because this is where I need to draw the line between established physics and theoretical speculation. Loop quantum cosmology is a serious research program. It has produced real mathematical results, but it is not an established theory of quantum gravity. It is one approach among several from ST. And the specific claim that black hole bounces produce new universes is a prediction of certain models within that framework. Not an established fact, not something we have observed, not something we can currently test, cross. But here is why I take it seriously enough to talk about it. The mathematical structure is coherent. The physical motivation is clear. And it connects to a broader framework of ideas called black hole cosmology, or, more provocatively, the hypothesis that our universe was born inside a black hole. The person who has developed this idea most extensively is the physicist Lee Smolin. And his argument goes something like this. If black holes produce baby universes through quantum gravitational bounces, then the universe that produced the black hole and the baby universe inside it are connected by something like inheritance. The baby universe inherits the physical constants of its parent universe, the values of the fundamental constants, the strength of gravity, the mass of the electron, the speed of light, the cosmological constant, all the numbers that define what kind of universe you live in, with small random variations like genetic mutation. And now here is the extraordinary implication. If different values of the physical constants produce universes with different capacities for forming black holes, then there is a selection pressure. Universes whose physical constants allow lots of stars to form, lots of heavy elements, lots of stellar evolution, and lots of black holes will produce lots of baby universes, which will inherit those productive constants. Universes with physical constants that do not favor black hole formation will produce fewer baby universes. Over many generations of universe reproduction, the multiverse will be dominated by universes with physical constants tuned to maximize black hole production. Smolin calls this cosmological natural selection. And here is what makes it genuinely interesting rather than merely speculative. The physical constants that maximize black hole production turn out to be very similar to the physical constants that are required for the existence of stars and planets and chemistry and life. Because all of those things require the same underlying conditions. Long-lived stars, heavy elements forged in stellar cores, stable atomic structures. The same constants that favor complexity in life also favor the formation of black holes. If cosmological natural selection is right, then the reason our universe has the physical constants it does is the same reason organisms have the traits they do. Because those constants were selected for over many generations of universe reproduction because they maximize reproductive success measured in black holes. We may be living in a universe that was optimized by a cosmic evolutionary process to be extraordinarily good at making black holes. And as a side effect of that optimization, extraordinarily good at making stars and planets and chemistry and life. We are not the purpose of the universe. but we may be a byproduct of the same process that shaped it. And the black holes we can observe with our telescopes may be the universe's reproductive organs, each one potentially seeding a new cosmos on the other side. I find that simultaneously humbling and magnificent. The universe not as a static backdrop for our existence, but as a living, reproducing, evolving entity. Each black hole a doorway, each singularity a potential birth, each new universe an experiment in physics run with slightly varied parameters. A cosmos that is, in some sense, alive in the deepest possible meaning of that word. But let me bring you back to the physics and to another radical proposal about what is inside a black hole. Because cosmological natural selection is not the only idea. And the landscape of theoretical possibilities is rich enough that I want to give you the full picture. Some physicists have proposed that the singularity resolves not into a bouncing baby universe, but into something called a white hole. And the distinction matters. A white hole is the time reverse of a black hole. General relativity's equations are time symmetric. They work equally well forward and backward in time. A black hole is a region of space-time into which things can fall, but from which nothing can escape. A white hole is the time reverse of that. A region of space-time from which things can emerge, but into which nothing can fall. Matter and light pour out of a white hole the way they pour into a black hole. White holes have generally been regarded as mathematical curiosities, solutions to Einstein's equations that do not correspond to anything in physical reality. Because while the equations allow them, there is no known physical process that produces them. You cannot make a white hole the way you can make a black hole by collapsing a star. But here is the twist. If the singularity inside a black hole is replaced by a quantum gravitational bounce, then the collapsing matter rebounds and the region of space-time that emerges from the bounce looks from the outside like a white hole. The black hole forms, matter falls in. Near the singularity, quantum gravity takes over. The collapse rebounds, and the matter eventually comes back out in a burst of white hole emission. The black hole and white hole are two faces of the same quantum gravitational process. Infall and outfall connected through a quantum bounce at extreme density. The physicist Carlo Rovelli and his colleagues have worked out some of the details of this scenario. And one of the intriguing predictions is about timescale. The quantum bounce inside the black hole happens very quickly in the time experienced by the infalling matter. But because of the extreme time dilation near the singularity, the emergence of the matter as a white hole takes an enormous amount of time as experienced by the outside universe, an astronomically long time. For stellar mass black holes, the emergence might take longer than the current age of the universe. Much longer. So white holes predicted by quantum gravity would not look like the dramatic explosions of matter you might imagine. They would be extraordinarily slow, dim, patient, nearly invisible. Could fast radio bursts be the signature of ancient small black holes completing their quantum bounce and erupting as white holes? Some physicists have suggested exactly that. Fast radio bursts are intense, millisecond duration bursts of radio waves coming from cosmological distances. We detect thousands of them. Their origin is debated. Most are probably caused by magnetars rotating neutron stars with extraordinarily strong magnetic fields. But the possibility that some fraction of fast radio bursts might be white hole eruptions has not been definitively ruled out. It is the kind of idea that makes you look at your data differently. Now, I want to bring you to something that has been generating enormous excitement in the theoretical physics community over the past several years. Something called the firewall paradox and its proposed resolutions. Because this is where the information paradox, the holographic principle, ER equals EPR, and the question of what is inside a black hole all collide in a single extraordinary conceptual crisis. In 2012, 4 physicists, Ahmed Almeri, Donald Marolf, Joseph Polchinski, and James Sully, published a paper that became known as the AMPS paper after their initials, Paxton. And what they argued was this: if information is preserved in Hawking radiation, as the holographic principle requires, then the Hawking radiation emitted late in a black hole's evaporation must be highly entangled with the Hawking radiation emitted early. The late radiation and the early radiation must be quantum mechanically correlated in a specific way that allows the information about what fell in to be reconstructed from the full radiation field. This is how information escapes, encoded in the subtle quantum correlations between early and late Hawking radiation. But here is the problem. The Hawking radiation is also produced at the event horizon by the splitting of virtual particle pairs. And for that process to work correctly, the late radiation must be entangled with the interior of the black hole, with the partner particle that fell in. And quantum mechanics has a rule, a deep fundamental rule called the monogamy of entanglement. A particle can be maximally entangled with only one other system at a time. You cannot share maximal entanglement. It is not like friendship. You cannot be maximally quantum correlated with 2 different things simultaneously. So the late Hawking radiation cannot be maximally entangled with both the early radiation and the interior. If information is preserved, the late radiation must be entangled with the early radiation. But then it cannot be entangled with the interior. And if it is not entangled with the interior, the partner particle inside does not exist as a smooth continuation of the exterior. The event horizon is not a smooth, empty region of space-time. It is a place where the entanglement structure of the quantum field is violently disrupted. A wall of high energy radiation, a firewall that would incinerate anything crossing the event horizon. The firewall paradox says we cannot simultaneously have all of the following things: information preserved in Hawking radiation. Quantum mechanics respected specifically the monogamy of entanglement and a smooth event horizon that freely falling observers cross without drama. At least one of those 3 things must be wrong. And all 3 have extremely strong theoretical support. This is a genuine crisis, a contradiction between things we believe for very good reasons. The proposed resolutions to the firewall paradox have been among the most creative and radical ideas in recent theoretical physics. And they all point in the same direction, toward the conclusion that the interior of a black hole and its exterior are not as independent as they seem. That what happens outside is not separable from what is inside. That the geometry of the interior is in some sense built from the quantum entanglement structure of the exterior. The most developed version of this idea comes from recent work on what is called the island formula and the page curve. Without going into the full technical details, the key insight is this. The calculation of the entropy of Hawking radiation must take into account contributions from regions inside the black hole, regions called islands. The interior of the black hole is not causally disconnected from the exterior when you do the full quantum gravitational calculation. It contributes, it is part of the story. And when you include the island contributions, the entropy of the radiation follows the page curve. It rises and then falls. Information is preserved. The paradox is resolved. But only if you accept that the interior and the exterior are entangled in a way that makes the distinction between them less sharp than classical physics suggests. And this connects back to ER equals EPR. The islands inside the black hole are connected to the exterior through the quantum geometry of entanglement, through wormholes, microscopic quantum wormholes, threading through the space-time geometry, connecting inside to outside. The interior is not isolated. It is woven into the exterior through the quantum fabric of space-time itself. What this picture is telling us is something profound about the nature of space. Space is not fundamental and packs. It is not the basic stuff out of which the universe is made. Space emerges. It is built up from something more fundamental, from quantum entanglement, from the correlations between quantum degrees of freedom that we do not yet fully understand, but that are beginning to come into focus through the study of black holes. John Wheeler, one of the great physicists of the 20th century, and the person who popularized the term black hole, used to talk about it this way. He said, space-time is not the stage on which physics happens. Space-time is one of the actors. And I think we are now beginning to understand what he meant at a level of depth that even Wheeler did not fully anticipate. Space-time is not just an actor. Space-time is a collective phenomenon, an emergent property of a deeper quantum reality, like temperature emerging from the motion of molecules, like sound emerging from the vibration of atoms. Space-time emerges from quantum entanglement, black holes. And black holes are the place where we can see that emergence most clearly. Because black holes are the place where the smooth fabric tears and the underlying quantum threads become visible. Now, I want to step back and give you the full view, the philosophical view, the view from as far out as I can take you. We live in a universe that has existed for 13.8 billion years. In that time, it has produced hundreds of billions of galaxies, each containing hundreds of billions of stars. Many of those stars have lived and died. Potter, and the most massive among them, have ended their lives by collapsing into black holes. They're estimated to be somewhere between 10 million and 1 billion stellar mass black holes in our galaxy alone. Billions. And at the center of virtually every large galaxy, including our own, there is a supermassive black hole with a mass of millions or billions of solar masses. The universe is full of black holes, extraordinarily full. And if each one of those black holes contains the seed of a new universe, then the multiverse is not just a theoretical possibility. It is the natural consequence of physics operating in the way we have every reason to believe it operates. Every black hole, a potential cosmos. Every stellar death, a potential birth. The universe reproducing itself through the very process of gravitational collapse that seems from the outside like pure destruction. And now consider the most extraordinary possibility of all, the possibility that points the arrow of this whole story directly at you. If our universe was born inside a black hole, then the Big Bang was a quantum bounce. The 13.8 billion year expansion of our universe that we observe, the cosmic microwave background radiation that we detect as a faint glow filling the sky in every direction. The large-scale structure of galaxies and galaxy clusters and cosmic voids that map the three-dimensional distribution of matter across billions of light years, all of it. The entire observable universe with its hundreds of billions of galaxies and its 10 to the power of 80 atoms in its one species on one planet that evolved the capacity to ask questions about its own origin. All of it emerged from a quantum bounce at a singularity inside a black hole in a parent universe that we cannot observe, whose physical constants we inherited with small variations, whose existence made our existence possible. We are the interior of a black hole looking outward at the cosmos we can see, unable to look back through the event horizon that surrounds us, unable to communicate with the parent universe from which we emerged, bounded on all sides by an event horizon that from the inside looks like the edge of the observable universe. The cosmological horizon beyond which light has not had time to reach us in 13.8 billion years. Our universe itself may be a black hole, seen from inside. Now here is what I find most moving about all of this. And I want to be precise about why I find it moving, because I think the reason matters. We are a species that evolved on the surface of a small rocky planet, orbiting an ordinary star in the outer suburbs of a galaxy that contains 400 billion other stars. We evolved to survive on savannas, to find food and avoid predators and reproduce and care for our offspring. Our brains were shaped by hundreds of thousands of years of selection pressure that had nothing to do with understanding quantum gravity or the information paradox or the holographic principle or the possibility that we live inside a black hole. And yet, here we are using those savanna brains, those fruit-picking predator, avoiding pattern-recognizing brains to reach into the deepest structures of reality, to write down equations that describe what happens at the center of a black hole, where the density is infinite and time itself breaks down. To discover that space-time might be woven from quantum entanglement, that information is indestructible. That every black hole might be a seed, that we ourselves might be the interior of one. That reach, that extraordinary, implausible reach from the savannah to the singularity is the most remarkable thing I know about being human. More remarkable than any individual discovery, more remarkable than any single equation. The fact that the universe produced creatures capable of understanding it, capable of looking at the most extreme objects it contains and working out from first principles what is happening inside them. That is not nothing. That is the universe becoming conscious of itself and doing it through us. We do not know what is at the bottom of a black hole. Let me be honest about that. The ideas I have described today are serious. They are mathematically grounded. They are actively being pursued by the best theoretical physicists alive, but they are not confirmed. The quantum gravity theory that would let us calculate with confidence what happens at the singularity does not yet fully exist. We have pieces, we have clues. We have the holographic principle and ER equals EPR and loop quantum cosmology and the island formula and the Page curve. We have a convergence of ideas that is pointing in a direction, but the final theory is not yet in our hands. I bend. And I want to tell you something about that. Something that I genuinely believe and that I think is the most important scientific attitude there is. The not knowing is not a failure. It is not an embarrassment. It is not a gap that we should be ashamed of or that we should paper over with confident assertions. And the not knowing is an invitation, the most exciting invitation in all of science. Because what lies on the other side of that not knowing is a theory of quantum gravity. That will be to general relativity and quantum mechanics what general relativity was to Newton: a deeper view, a wider lens, a more complete picture of the machinery of reality. And when we have it, when some physicist somewhere working on some combination of these ideas cracks the problem, the picture that emerges will be strange. It will be counterintuitive. It will require us to revise our deepest assumptions about the nature of space and time and matter and information. And it will be beautiful in the way that only truth is beautiful, in the way that only a deep, correct idea about the nature of reality can be beautiful. Because the universe at its deepest level has always turned out to be more elegant and more unified and more surprising than we expected. Every time we have peeled back a layer of reality and seen what was underneath, we have found something more magnificent than what we saw on the surface. The singularity is the next layer. The black hole is the next door. And physics is standing at that door right now with its hand on the handle, working out how to turn it. So the next time you look up at the night sky and you think about the black holes that are out there, the stellar mass remnants scattered through our galaxy, the supermassive monster at our galactic center, the billions of black holes and billions of other galaxies across the observable universe, I want you to see them differently, not as voids, not as absences, not as the places where stars went to die, but as the most information-rich objects in the cosmos, as the laboratories where the universe works out the deepest laws of physics as the potential seeds of new spacetimes, as the places where the quantum threads from which space itself is woven are pulled tight enough to see every black hole a mystery, every mystery an invitation, every invitation a chance to understand something true about the nature of existence. And this remarkable, improbable species on this pale blue dot in this ordinary galaxy, in this universe, that may itself be the interior of a black hole. We are the universe's way of accepting that invitation. That is not nothing. That is everything. Meditate on that